Newton's laws. What causes an acceleration? The change in velocity must be due to an interaction between the body and something in its surroundings. An interaction that causes an acceleration of a body is called force, which is, loosely speaking, a push or a pull. The relationship between a force and the acceleration it causes was first understood by Isaac Newton, and the study of that relationship, as Newton presented it, is called Newtonian mechanics. Great scientist, Newton, everybody knows. Newtonian mechanics does not apply to all situations. If the speeds of the interacting bodies are an appreciable fraction of the speed of the light, we must replace Newtonian mechanics with Einstein's special theory of relativity. If the interacting bodies are on the scale of atomic structure, for example, they might be electrons within an atom, we must replace Newtonian mechanics with quantum mechanics. Physicists now view Newtonian mechanics as a special case of these two more comprehensive theories. Still, it is a very important special case because it applies to the motion of objects ranging in size from the very small, almost on the scale of atomic structure, to astronomical objects such as galaxies and the clusters of galaxies. Newton's first law. Newton's first law. If no force acts on the body, then the body's velocity cannot change. That is, the body cannot accelerate. You do not need a force to keep a body moving with constant velocity. Soccer athletes are those people who apply the Newton's first law most skilled. Inertial reference frames. Newton's first law is not true in all reference frames, but we can always find reference frames in which it and the rest of the Newtonian mechanics is true. Such frames are called inertial reference frames, or simply inertial frames. An inertial reference frame is the one in which Newton's law holds. Vice versa. If Newton's laws hold, then this frame is an inertial frame. We usually assume that the Earth's ground is an inertial frame, and that measurement of forces and accelerations are made from it when Earth's rotation can be neglected. See, only we neglect the Earth's rotation effect, then we can treat it, the Earth's ground is an inertial frame. Don't forget this one. It's just, strictly speaking, the Earth's ground is a non-inertial frame because the Earth is rotating.
If a glider is at rest on a track and the track is shifted from side to side, the glider will move with the track. Air is now forced through holes in the side of the track so that the glider is supported on a cushion of air. What will happen now if we shift the track from side to side with the air turned on? The glider is now motionless. If we give the stationary glider a single push, it moves at a constant speed after the force is gone. We'll try to remove the tablecloth from under these dishes without making a mess. How? By yanking the cloth out very fast. Pull slowly and the table setting moves. This will have to be done much more quickly. A metal tube wrapped inside the loose edge of the cloth provides a firm grip for a fast pull. When the cloth is yanked out fast, the dishes barely move.
Could you remove this pizza pan from under these eggs without touching or breaking the eggs? If the eggs could be made to drop straight down, they would land in these water-filled beakers and would survive intact. By striking the pizza pan hard with this broom handle, the pan will fly out, allowing the eggs to drop straight down into the beakers. Let's try it. The pizza pan shot out so fast that the eggs barely moved. Let's watch again in slow motion.
A ball given a push inside an aluminum ring rolls around inside the ring. When it reaches this gap, which path will the ball follow? Will it follow this path, or this path? The ball follows a straight line in the same direction it was moving at the point of escape. Its path is tangent to the circle at that point.
Newton's second law. First, a force causes the acceleration of a body. We now wish to define the unit of force carefully in terms of the acceleration that it gives to a standard reference body. As the standard body we use, or rather we imagine that we use, the standard kilogram. This body has been assigned exactly a mass of 1.0 kilogram. We put the standard body on the horizontal frictionless table and pull the body to the right so that by try and error, it eventually experiences a measured acceleration of 1 meter per second per second. We then declare, as a matter of definition, that the force we are exerting on the standard body has a magnitude of 1 Newton, abbreviated capital N.
We will use a glider floating on a cushion of air and a light spring to demonstrate how a constant force from a spring can accelerate the glider. The spring is attached to the end of the glider, and a marker stick is attached to the top of the glider to indicate the extension of the spring. When the spring is pulled out, it pulls on the glider with a constant force. The force from the spring accelerates the glider. Here's the same acceleration repeated, with dots on the screen recording the position of the glider every half second.
In general, if our standard body of 1 kilogram mass has an acceleration a, we know that force F must be acting on it, and that the magnitude of the force in newtons is equal to the magnitude of the acceleration in meters per second per second. A force is measured by acceleration it produces. But acceleration is a vector quantity with both magnitude and direction. Is force also a vector quantity? The answer is yes. Forces are indeed vector quantities. They have magnitudes and directions, and they combine according to the vector rules.
This cart on an incline is acted on by 3 forces: a downward gravitational force, a force along the direction of the incline supplied by this weight and string, and a force perpendicular to the incline provided by the incline itself. A mass hanging over this pulley will provide a force equal to the force from the incline. At this point, do we need the incline? The incline is no longer needed. It can be removed and the cart will stay in place.
The strings tied to this ring exert forces on the ring. Masses hanging from the ends of the strings provide the actual force. A 500-gram mass on this string, an 866-gram mass on this string, and a 1,000-gram mass on this string. If we pull the ring away from the center, it returns to its original position. The ring is in stable equilibrium. These vector arrows represent the force exerted by this string and the components of that force in the horizontal and vertical directions. Here is a similar analysis for the second string. The horizontal components of the two forces are already in balance. The third weight must equal the sum of the two vertical components, or 9.8 newtons.
Henceforth, we shall use bold-faced letters, most often capital F, bold font, to represent forces. And we shall use the symbol sigma F for the vector sum of several forces, which we call the resultant force or the net force. As with other vectors, a force or a net force can have component along coordinate axis. Finally, we know that Newton's first law is no force on the body, but also when the net force is equal to zero. So the Newton's first law can be rewrite as if no net force acting on the body, sigma F equal to sigma net equal to zero, then the body's velocity cannot change. That is, the body cannot accelerate. Mass. Everyday experience tells us that a given force produces different magnitudes of acceleration for different bodies. We can explain how to measure mass by imagining a series of experiments. In the first experiments, we exert a force on our standard body, whose mass m is defined to be 1.0 kilogram. Suppose that the standard body accelerates at 1.0 meter per second. We can then say the force on that body is 1.0 Newton. We next apply that same force. We will need to some way to be certain that it is the same force to a second body X, whose mass mx is not known. Let us then make the following conjecture. The ratio of the masses of the two bodies is equal to the inverse of the ratio of their accelerations when the same force is applied on both. So mx over m equal to a over ax. Same force applied. Okay, this is conjectures. Our conjecture will be useful, of course, only if it is continue to hold when we change the applied forces and the standard body m to other value. This one ought to be true because we, in this measurement condition, we have two variables. One is the force. Before we use the standard force, 1 Newton. Now we change to other force. See whether this true. Or we change the standard. Instead of 1 kilogram, we use the other number. And we find we change the standard, we change the force, and we find this AX is the same. I'm sorry, MX is the 3. MX is the 3. So many experiments yield similar result. That means MX is the same thing. Indicate that our conjectures provide a consistent and reliable means of assigning a mass to any given body. So we can assign a mass to anybody, okay, just by this experiment. Our measurement experiment indicate that mass is an intrinsic characteristic of a body. That is, a characteristic that automatically comes with the existence of the body. They also indicate that mass is a scalar quantity, no direction, only magnitude. The mass of a body is the characteristic that relates a force on the body to the resulting acceleration. The net force F net on the body is the vector sum of all the external force. F net equal to sigma F external. Newton's second law. The net force on the body is equal to the product of the body's mass and the acceleration of the body. F net or sigma F equal to ma. We see A is a vector, so we can write it in vector form: AXI plus AYJ plus ACK. Remember, all these forces must be on that body, okay? If F is not on that body, it's nothing to do with situation. 2. Vector sum. This is a vector sum. It's not algebraic sum, vector sum.
If a string hanging over a pulley is loaded with a small weight, it provides a force which can accelerate a glider floating on a cushion of air. Here is the same acceleration, with the position of the glider marked by dots at half-second intervals. If the force is doubled by doubling the hanging mass, how will that affect the acceleration of the glider? The dots are more widely spaced, so the acceleration has increased. If the same hanging weight is now used, but the glider's mass is doubled, how will the acceleration change?
With double force, double mass, see what happens. Acceleration should be the same.
Here is the new acceleration. Here are all 3 accelerations and the force and mass data for each.
They're the same.
This device is known as an Atwood's machine. 2 equal masses hang on either side of a string passing over a pulley. Since the masses are equal, there is no net force to accelerate the masses, and they are in equilibrium in any position. A small rider is now added to one of the large masses, and the system begins to move. How could we best describe this type of motion? Since there is a constant unbalanced force on the system, it is accelerated. The traces left behind each half second in this segment show the acceleration. If the mass now passes through this ring so that the rider is picked off, how will the motion of the masses be affected? The masses now move with the constant velocity. Here is the same sequence repeated with 2 riders added to the large mass.
When this large rock is struck with a hammer, it barely moves. Why does this rock behave so differently? The first rock is real and very massive. The force of the blow barely accelerates it at all. The second rock is made of low-mass foam rubber. The same blow from the hammer on this rock causes a very high acceleration.
Sigma F equals F net equal ma. Newton's second law. We know sigma F is a vector, so it has 3 components. F net, the same thing. Have F net xi, F net yj, F net k, and A is a vector. So ijk is a unit vector along 3 axes. They had nothing to do with relationship. So we compare the coefficient in front of I, j, and k. We get sigma fx equal to max. Sigma fy equal to may, or sigma mfz in front of k equal to mack, or f net x equal to max, f net y equal to may, f net z equal to mz. These equations relate the 3 components of the net force acting on the body to the 3 components of the acceleration of that body. 3 components are independent with each other. Well, look at this one. The acceleration components along a given axis is caused only by the sum of the forces component along the same axis, as not by force component along some other axis. Look at this. AX is only related to FX, nothing to do with FY or FC. And FC is only related to AAC, nothing to do with AY and AX. You should know that Newton's second law enclosed the formal statement of Newton's first law as a special case. For metric system unit, 1 Newton equal to 1 MA, 1 kilogram meter per second per second. Unit in Newton's second law. Unit. Force, we use a Newton. Mass, we use kilogram. Okay. Acceleration, meter per second per second. Okay. 1 Newton equal to 1 kilogram multiplied by 1 meter per square per square. Newton's third law. When 2 bodies interact, the forces on the bodies from each other are always equal in magnitude and object interaction. Relax. A book is lying on a crate, C. Okay. We have 2 forces. One is the force CB, force acting on the crate by book B. Another one is FBC, the force acting on book by crate. They are equal and opposite, but they never cancel out. Why? Because they acting on different objects, so they never cancel out. FBC equal to minus FCB, the vector, direction, magnitude. Forces come in pairs, also pairs. Commonly, one of these factors, it doesn't matter which, is called the action force. The other member of the pair is then called the reaction force. They never cancel with each other. Now we look at this cantilever at rest on the table. It exerts 2 forces. okay? It's at rest, so the sigma F equal to 0. You have two forces acting on it. At some points, some students say, hey, you see, this pair cancel out. These forces is cancelled out. They are equal in magnitude and opposite direction, acting on the same cantaloupe. Look like what they are pairs. This one, acting on the cantaloupe by Earth, is paired with acting on the Earth by cantaloupe. And this force acting on the cantaloupe by table is paired with this force acting on the table by cantaloupe. Okay, they are different pairs, but they cancel out because they acting on the same object. In this case, cantaloupe.
If one object pushes on a second object, the second object accelerates. But what about the object doing the pushing? Does it also accelerate? We will use these gliders floating on an air track to find out. This spring bumper will provide the force from the first cart on the second. If we tie the carts together with the string so that the first cart is pushing on the second, then burn the string, what will happen to the first cart? Both carts accelerate. When one object pushes another, the second object pushes back. For every action, there is an equal and opposite reaction.
We'll use this radio-controlled car and a board on rollers to demonstrate action and reaction forces. The car and board are both initially at rest. When we start the car moving to the left, the board moves to the right. The car exerts a force on the board, and the board exerts an equal and opposite force on the car. This animation shows the forces that act between the car and the board.
This small cart has a motorized fan mounted on top. When we turn on the fan, the cart moves off to the side. If we put a sail on the cart and turn on the fan, which direction will the cart move? The cart doesn't move at all. If we blow on the cart with a fan which is not attached to the cart moves in the direction of the airflow. This animation shows the force acting on the cart without the sail. Here are the forces acting on the cart when the sail is in place. And this is the force which acts on the cart when the external fan is used.